Okay, so let me just say one thing. We actually only have one slide to go through today about a function on the calculator and also some notation to help support the things we're now learning. We're able to now find the slope of this curve. We said the limit as h goes to 0 of f of x plus h minus f of x all over h. And if we continue this process, instead of writing the word slope here, we might like another thing to say. And so our notation, the function we get down here, if we leave the x in, the function we get, like Stephen got here, it's 3 over 3 plus x plus 3 quantity squared. That function, maybe we need a name for it. Well, it kind of goes with f. If we call it the original function f, then it kind of goes with f, so we want to have some notation for that. So if you've seen your friends in calculus, you know that we will often write it that way, f prime of x. So that says that this like relates to f somehow. What is it? Well, it's the slope buddy function for f, isn't it? Like f is responsible for giving us heights. You give me a horizontal position on the function, and I give you like the vertical position. That's what f does, right? Gives me the height that I live at on the function. Well, f prime, you give me a value of x, and I give you the slope at that place on the function. So it has a role too, and we call it f prime. In fact, I have that notation on this slide also. We also call it the derivative. We've been holding out to say, and we've been saying the instantaneous rate of change at a point. Or we've been saying the slope of the tangent at a point, or whatever. But we can actually come out and use the word. It's the derivative. And this is the definition of the derivative. We've been using it now for a couple days, and we can say it.
So we already know the derivative.
Huh?
So we already know where it is.
You do know that this. Yeah, this is the derivative of the thing we found in the warm-up, 3 over x plus 3 squared, that thing. That's called the derivative function for f, right? F prime of x would be one way to write it. I'll show you another way in a second. Sometimes, though, I just want to be clear, sometimes we are called on to do this algebra, and so we might be, but sometimes that's not possible. Sometimes we don't have the function, or it's computationally infeasible to compute the derivative. So keep in mind that we still have a lot of times a task to estimate the slope of a tangent. Sometimes we need to do that from a graph, like you've been doing. You drew tangent lines. Sometimes you need to do that from a table of values, which we haven't done a lot of, but we'll do today. Are you staying or something?
No.
Okay. Or from or with a function, which we now can think about too. And we'll think some more about how to do that as well today. Remember, this works both ways. We showed it in blue and on green on the board on the warm-up. You can either think about this derivative function here as being something that can generate slopes. That's this beautiful thing that Stephen did. Or it can be the thing that, or you can just calculate a numerical value of a slope at some point, right? They're both, if you let x actually take on the value -1, for instance. Okay, so we have kind of two ways of thinking about it, maybe, if you want. All of these things could be done to graph the table of values. Oh, sorry. I was going to add this. So we often write f prime of x, that's Newton's notation, or a notation that we'll also really, really like a lot in this class is dy dx is what we'll read that out loud as. But the reason we kind of like dy dx is because it's another symbol that means exactly the same thing, is because it should remind us of something. Remember what this is here? Remember, it's a slope calculation. And when we did it with a secant line, that is without the limit as h goes to 0, we just calculated it between 2 points. What's the formula from like algebra 1? Isn't it delta y over delta x? And so in math in general, but especially here, right now, whenever we say dy, we mean an infinitesimally small change in y over an infinitesimally small change in x. So we kind of like the Leibniz notation for other reasons too. But one of them is that it kind of reminds us of our roots, like where we came from. This is still like a difference quotient, isn't it? It's still we're still like dividing the change in y divided by the change in x, except now they're like infinitesimally small. So we kind of like that notation as well. The other thing we like about it too is that it makes really clear, very explicit, what the independent and dependent variables are that we're taking the derivative of something with respect to something. And that will become really, really useful when we have an equation that has lots of variables in it. And I'm asking you, take the derivative of this equation, please, of v with respect to t or something. And there are all sorts of other letters in there. And you might want to keep track of what am I taking the derivative of and with respect to what. So right now I think we'll probably stick with f prime for a little while. I mean, both, we'll use both. But you'll soon see why Leibniz notation is actually really cool too. Okay, I promise. Notice too that sometimes we ask you to estimate these things with a calculator. Sometimes we ask you to estimate the tangent line slope without a calculator, right? So all these are things that we can ask with or without a calculator. Let me carve out why I have check marks there. On your calculator, just so you know too, if you guys would actually try this with me real quick. If you here, let me pull up my calculator too, because I think this is worth doing. I'm going to use the warm-up as the example. Okay, so I want to show you a couple things, a couple button pushes on the calculator here. Where'd my calculator go? See if I can find it. Do we see it anywhere? Where'd it go? Sorry, my board doesn't work really very well. Oh, it is off to the side here, isn't it? Good idea. Okay. All right, we're back. Okay. So go ahead and actually, why don't we put in y1? You wouldn't have to do this, but I think just for the sake of this discussion too, it might be helpful to have this in y1. What was it? X divided by x plus 3. Okay. So do that. And then one way to calculate the slope of the tangent line at -1 would be to actually do the following, right? y1 of -1 plus 0.001, how about, right? Would that be a good h value? That's close to 0, isn't it? Okay. Minus, actually, I think there's a quicker way, isn't there? y4, yeah, f4. y1, I'm just saying you can do alpha, if you're on this calculator at least, you can do alpha trace, f4 menu, I don't know, whatever. Do you know how to get the y1 on your calculator? One way or another, on whichever calculator you're using. Okay. Divided by the difference between the two of them. What is -1 plus 0.001 minus -1? Well, of course, it's just 0.001. It's our choice of h. All right, so that should be a good estimate of the slope. Do you agree? Let's see if we get something close to 3/4. Yes. You want a better estimate? Of course you do. Let's add another 2 zeros in there. Let's make it 0.00001. Ah, there we go. That's a really good estimate, isn't it? And we can get without, so if all we need, guys, if all we need is the slope of the tangent line at one particular value, then we can do an estimate very precisely on the calculator just by doing this. Now, even quicker than this, I just want to make sure I reveal that the thing I'm about to show you is not like magic. All your calculator is doing this for you really quickly and with a really, really small h value, okay? So that's all that we're going to do. It's math, number 8, n derivative, which stands for numerical differentiation, okay? Numerical derivative. Now, it's using, you should recognize this is Leibniz notation. It's gonna, now, some of you actually have on your calculator if you have the old firmware on your calculator, then it will show up exactly the way I have it on the screen here. I haven't updated my slide. But up here, I'll show you on your new calculators how it works, okay? What's the variable that you're taking the derivative with respect to? Well, you might not think that we'll ever use anything other than x, but yeah, we are using x right now. Okay, so put an x in there. What's the function that we want to use? Well, you could actually type in x divided by x plus 3 there. Or, since we already have it in our calculator, we can put it in with y1 too, right? And then at what x value? This vertical bar is a notation we'll use in class 2 at some point if we haven't used it yet, I don't think. It just means, hey, calculate this thing And evaluated at, that bar means evaluate at x equals whatever. So in this case, we want -1. And then see that it gives you 0.75. And again, notice why is there garbage at the end? Again, because it's just a machine. It doesn't know calculus. It is in fact doing exactly what we're doing, just with like a very small h value. Just keep in mind my quote up here, right? Calculators are just dumb machines, okay? They can only calculate, they don't actually, it's not demonstrating understanding, okay? It's just doing a difference quotient, just like we did, okay? It's just a little faster to do it that way than to choose, whatever. So that's a cool tool for estimating the slope at a point as well. But what do you need for this? You need the function. Like if I show you a picture or something like that, that doesn't help. If I give you a table of values and it only has certain y values given to you, that doesn't help, right? In order to do this, we have to be able to call up the value of the function at a point and also the value of the function at 0.00000001 away. And that might not be something we have on demand, right? But if you have access to the actual function, which we do, there it is, then you can use nderiv. Okay. So anyway, nice tool to have in your back pocket as you do some of these problems. I'm sure there are other things I'll want to say. Well, one thing I want to say too, you haven't seen any tables yet, but I'm going to give them to you now. What would you do if you wanted to calculate from a table that the instantaneous rate of change from the table? What would your best estimate be? That's all you can do is estimate, you don't know. Like this first one on the top here, and then I'll let you just work on these here. But look at that first one, like how do you calculate this? An estimate on part number 1, part C, it's going to ask you for, from the table, what's your best estimate on part C of the slope at t equals 2.9? And what would you use there? Yeah. I'm sorry. Anybody want to suggest a value to use, especially considering the approaches we were just taking? Ideally, what would you want to use? You'd want to use 2.9 and 2.9000001 or something, right? We don't have that though, so what would you like to use instead? Yeah, 2.9 and 2.8 you said? Or what did you say? Or 2.95? Or alternatively, you could use like 2.8 and 2.95, right? Or you could use 2.8 and 2.9 and 2.95 and 2.9 and then average the two answers or something like that, There are a couple different ways you could do it. If you're at the end point of a table, like if you wanted to estimate the slope at 3, you definitely want to use 2.98 and 3. Yeah, so 2.95 is actually closer, isn't it?
Yeah.
So let's use 2.9 and 2.95 because that's the closest we can get. Right? I think that is probably the best way to do this one. Occasionally they'll be equal, and you might just make the choice or something. So, okay, so that's the only other thing I wanted to say about tables, right? So, I don't know. If we have questions along the way, then let me know, and we'll go over some of these problems in a minute if you need to. Any other thoughts, questions before I let you play around with this? Yeah. Cool. There's